Okay, so today we're going to start chapter 7, which is on alcohols. And there will be a lot of chapters like this one where we basically go over a certain functional group. And we learn properties of compounds that have that functional group. We learn properties and characteristics. We learn ways of making compounds that have that functional group in it. And we also learn reactions of compounds with that functional group. And that's certainly what we're going to cover here. I've set aside 3 days for chapter 7. So that will be today, Friday, and Monday. I think that will be plenty of time. I am embarrassed at ending class early, like I have been doing. But at the same time, I really like the relaxed atmosphere. I don't like feeling like I have to push ahead at some ridiculous rate. If we err on the side of going slowly, I would rather do that than err on the side of going too quickly. And the sense I'm getting is people don't mind if we end 5 minutes early or something like that. I don't know why it's happening so often, to be honest. When I made the new schedule this term, I had taken out 2 chapters that I had otherwise covered during the semester and replaced them with 2 others. Now, one of those chapters was the heterocycles chapter. That was really short. We covered that in 1 class day easily. So I don't know where all this extra time is coming from. I don't feel like I'm forgetting anything. But be that as it may, we'll continue with the schedule. The other chapter, of course, I added was polymers. I think polymers are just too important for any career and daily life for you to come out of a class covering organic chemistry without knowing at least something about polymers. And if any of you are in sort of a field more related to engineering or material science, I think you'll also find that interesting. So that's what we're going to end with, is the chapter on polymers. But this chapter is in alcohols, and I have 3 class days set aside for it, which is today, Friday, and Monday. The plan then is on Wednesday, a week from today, we'll start chapter 9, which I believe is on aldehydes and ketones, though I'll double check. Yes, aldehydes and ketones. And you know what? I think I found the flaw in my schedule. It doesn't ever mention 9.1 through 9.4, and yet I'm sure we're covering it. All right, I just decided to start going a little bit faster because we need to cover the beginning of chapter 9 as well. So that might be a mistake. So we might not take all 3 class days to cover alcohols. We might just go into Wednesday and then stop on alcohols, or rather go into Monday and then stop. And then I might be starting chapter 9 on Monday. Maybe we'll cover 9.1 to 9.4 that day. I'm really glad I noticed that now as opposed to next week. But yes, I think we, as far as I recall, I'll double check for you guys. But as far as I recall, we're covering all of chapter 9. Anyway, so as usual, whatever we cover on chapter 9 before the exam will not be on exam number 3. That'll be in exam number 4. And then the 3rd exam should go pretty much like the previous one. I plan to administer it pretty much the same way. Let me look. It should be 7, 13, 15, 18. So remembering that some of those chapters are super short, like 13 we covered in 1 day. So we'll finish chapter 7 long before Friday. That's not going to be a problem. I'm just saying that there won't be any chapter 9 on that exam. That'll be in exam 4. Good. Anything else I should be made aware of? I feel like I just discovered a serious flaw in my syllabus. Well, at least we discovered it ahead of time than too late. That's good. Okay, because I don't want to rush through that material either. So I believe I mentioned last time, and there were some questions about it, how alcohols are an organic derivative of water. And what I mean by that is if you take water and you replace one of the H's in water with some alkyl group, R, then you get an alcohol. And if you do that same procedure twice, then you get an ether. So ethers are also organic derivatives of alcohol. That, by the way, was one of the chapters I took out, was the chapter on ethers. You want to know the major part of the content of the ethers chapter? It's ethers don't do very much. They're quite inert. Great, now we've covered that chapter. There's very little else to say besides that. That is not true for alcohols. Alcohols are pretty reactive under the right conditions, and there's a lot of different reactions that they can undergo, which I believe we'll probably be getting to mainly on Monday, perhaps to some extent on Friday, but probably mainly on Monday. And that's why, as I think I mentioned the last time, alcohols hold this very central place in organic synthesis. I wouldn't be surprised if half or more of all organic syntheses that are that are done in the industry start with an alcohol as the starting material. The same is true of hydrogen sulfide, by the way, H2S. If you replace one of the hydrogens in hydrogen sulfide with an alkyl group, you get a thiol. These used to be called mercaptans, the MERCAPTAN. That's the older name. No one really uses that anymore. Now we call them thiols. And if you do the same type of thing again, then you get a sulfide. Sulfides can also be, yeah, my syllabus says no chapter 9 content will be in exam 3. Yes, that's what I said. Chapter 9 will not be on next Friday's exam. That'll be in exam 4, not 3. So yes, that's right. We're starting it though, just to leave a little bit of extra time to study. And I see I actually made a mistake in the syllabus. There should have been another class day on chapter 9. So I'm going to try to move things around and get us through chapter 7, maybe a little bit sooner so we can start chapter 9 a little bit earlier. But I'll be clear about that when we get there. I'll say we're done with chapter 7 and the next material will not be on the exam. Now we are not done with chapter 7. We're just getting started on chapter 7. But we're not gonna cover ethers and sulfides so much here, although I would say all of these functional groups, thiols, sulfides, alcohols, and ethers are one you find in biologically related compounds, in all sorts of pharmaceuticals and other compounds of general consumer use, let's say. So, but we're going to run into all 4 of those functional groups when we get into amino acids for sure. We're going to do a chapter on amino acids and polypeptides. And then certainly alcohols are going to show up when we get to the chapter on carbohydrates, which we're also going to cover. What else can we say in terms of properties of alcohols? Alcohols certainly are polar, just like water is. Alcohols, I didn't draw them that way. I didn't draw them using the correct geometry, but alcohols will have an sp3 hybridized oxygen, just like water does. So these are still built on a regular tetrahedron. We call that geometry bent. We call the molecular geometry bent, meaning that the oxygen is at the middle of a regular tetrahedron. On 2 corners of the tetrahedron are the 2 hydrogens, and on the 2 other corners of the tetrahedron, you find the 2 lone pairs in oxygen. And the same is true of hydrogen sulfide, by the way. And so these organic derivatives of those compounds share that shape with their inorganic parent compounds, water and hydrogen sulfide. So the geometry around the carbon-oxygen-hydrogen bond angle is again going to be bent in both alcohols and thiols. They're still going to be built on a regular tetrahedron. So it's a natural consequence of those oxygen and sulfur atoms being sp3 hybridized. I should also mention, and we may get to this as soon as today, that alcohols are also amphoteric, like water. That's a nice word to remember from your Gen Chem. Amphoteric means that it's able to act as either an acid or a base. And in that sense, alcohols are no different from water. Water is also amphoteric. Ammonia, NH3, is amphoteric. So it's not that uncommon a property to run into. So alcohols and thiols are both amphoteric. Alcohols may be more so, but thiols, I think, to some degree also. Let's see. So much for properties of alcohols, and to some degree, we'll talk about thiols a little bit also. What about naming alcohols? Turns out naming alcohols is quite straightforward. If you can name an alkyl halide, which I think you can if you can name an alkane, I think I already told you guys that when you learn how to name alkanes, you've learned at a conservative estimate, 85 to 90% of what you need to know to name anything else. And naming alkyl halides is something we also practiced. Naming alcohols is very, very similar to naming alkyl halides. You still want to find the longest possible alkyl chain if it's an acyclic compound, or you want to look for which of the cycloderivatives if it's a cyclic compound. And use the same kind of numbering. You just want to make sure if it's an alcohol that you end with the suffix ol, O-L. And, you know, for instance, let's do some naming here. For instance, you would call this compound cyclohexanol. I guess you could call it hydroxycyclohexane, but that'd be kind of weird. I don't think anyone would really call it that. I think people would refer to that molecule as cyclohexanol. So you see again that ol ending. That's typical for alcohols. If you had something like this, well, you've got a 5-carbon chain, so it's going to be named as a pentane or a pentanol. And all you need to do is say where the OH group is on the alcohol. Since it's on the 2nd carbon of 5, we're going to call that one 2-pentanol. And there are some compounds that have more than one correct name, generally because they have a really old name that has stuck. Maybe it got named 100 years ago or more. This one here, benzene ring CH2OH, is generally named benzyl alcohol. You could, I suppose, call it phenyl methanol, but people would give you the side eye if you called it that. But it would not be wrong. But we call it benzyl alcohol. That's the most common name. So sometimes there's multiple correct names. You know what? Let me skip over categorizing alcohols and go straight to phenols, because we also need to know how to name phenols. Remember, phenol is hydroxybenzene. You learned that in chapter 4. So that's another confusing thing, because this looks like it should be benzyl alcohol, but it's not, it's phenol. Benzyl alcohol is the extra carbon in it. It's benzene ring CH2OH. So that's one of those old names that we're just stuck with. It's been around for decades and decades, probably over a century. But phenol is hydroxybenzene. And naming phenols is pretty straightforward. This compound here, for instance, just to give you an example, you could call that one 3,5-dibromophenol. Because carbon 1 is understood to be the one with the OH on it. And then you can keep counting around in either direction. It's not going to matter. You'll get the same answer. 5, 6. There you go. So whether you go clockwise or counterclockwise, in this case, it's 3,5-dibromophenol. To give another example and remind you about naming aromatic compounds, what if we had this guy here? That one you could call either 4-ethylphenol, or you could also call it p-ethylphenol for para. Both names are equally correct. I have zero preference for either one over the other. They are equally correct. And what if there's already another functional group on the benzene ring, such as it's benzaldehyde or benzoic acid or something like that? Well, if you had an OH group on a benzoic acid, then you would call the OH group hydroxy, and you would name it as a benzoic acid derivative. So this one would be either 2-hydroxy benzoic acid, or you could also call it O-hydroxy benzoic acid. And once again, I consider both names to be equally correct. And actually, I'm kind of lying to you. The real name for this compound is salicylic acid. I don't think I really care if you know that. Salicylic acid. You might have heard of it, though. Salicylic acid is isolated from the bark of the willow tree. It's been known for literally thousands of years to be something that lowers fever and decreases pain. And as you would guess, it's a very short walk from salicylic acid to acetyl salicylic acid, otherwise known as aspirin. And so a little company called Bayer that you might have heard of did fairly well making aspirin and has done for many, many decades. But I don't really care if you memorize it's called salicylic acid. Some of those common names may be common to an organic chemist, but are maybe not common to sort of the general public. Certainly for our purposes, I would be fine with either of the other names. If you also know it's called salicylic acid, that will make me happy, but I don't really care if you memorize that. Let's see. Good. Any questions so far then? Oh, sorry. It's named as benzoic acid because without the, I'm putting my finger on the screen, but that does nothing for you guys. If the OH weren't there, it would be benzoic acid. So with the OH, I think you have to name it as a benzoic acid. I don't have like a nice name for the carboxylic acid group. I think you would want to name it as a benzoic acid. Yeah, just want to make sure I answered your question. Yeah, that's named as a benzoic acid derivative. And if instead of a carboxylic acid, it had an aldehyde functional group, it would be 2-hydroxybenzaldehyde, for instance. If there were a methyl group there, instead it would be 2-hydroxytoluene. Or actually, that one I think you could call 2-methylphenol. Like I said, there's sometimes more than one correct name. Oh, can I repeat the question? Yes, I should have remembered to do that without being. The question was about whether we named this compound as a benzoic acid or as a phenol. And I said it's easier to name it as a benzoic acid derivative. I should have known that. You're right. You should have not had to remind me. Sorry about that. Okay, so let's make some more space. Alcohols in general come in a few different flavors. There's only one methyl alcohol, which is methanol. It's the only one of its type. You can call it methyl alcohol. Everyone will know what you mean. Beyond that, we have 3 types of alcohols. Actually, let me first, I want to move that down a little bit. Whoops. Ooh, that wasn't what I meant to do at all. Control Z. Oh, well, I'll just move it down a little bit. If we replace one of those hydrogens on the methyl group with some alkyl group, then alcohols, you get an alcohol of this type. And that one we would call a primary alcohol. Doesn't matter what R is. I think we went through this with amines too, didn't we? Primary amine, secondary amine, tertiary amine. Same thing is true of alcohols. If there are 2 R groups on that carbon, then we would call that a secondary alcohol. And finally, if there's 3 R groups there, these R groups can be the same or different, doesn't matter. We call compounds of that type tertiary alcohols. And it's just helpful to be able to recognize each different type, especially because once we start getting into reactions of alcohols, you're going to find that there's some reactions that primary alcohols can undergo, but secondary alcohols can't, or secondary alcohols can undergo, but tertiary alcohols can't. So that's why it's important to know this type of classification of alcohols. There's basically 4 types. There can be no such thing, by the way, as a quaternary alcohol, because to make a quaternary carbon, you would need to take away the OH group, and then it would no longer be an alcohol. So that's why there's no such thing. But there's only one methyl alcohol, which is methanol. Besides that, you've got primary, secondary, and tertiary alcohols. So that, I think, is an important classification of alcohols to have down. It's going to be useful to be able to categorize alcohols. Good. So let's see. Next thing we need to talk about is hydrogen bonding. And we've talked about hydrogen bonding a fair bit so far. You're aware that hydrogen bonding exists in molecules like water. So maybe now I'll do a little bit better job of showing the water molecule as being bent. So it's a phenomenon that exists between separate molecules of any given compound. And it causes more ordering of the molecules, and it means that you have to put in more energy in order to separate molecules from one another. So hydrogen bonds are not covalent bonds. Hydrogen bonds turn out to be somewhere in the order of 5 to 10% as strong as most covalent bonds. That sounds like a reasonably important statistics. H bonds, 5 to 10% as strong as covalent bonds. At the very least, if it was important enough for me to say, it should be important enough for me to write it down. So the reason I have to give a range is not all covalent bonds are created equal. They have strengths over a pretty wide range also. But it means if you consider most covalent bonds to be a few hundred kilojoules per mole, then hydrogen bonds are generally in the area of around 20 kilojoules per mole, maybe 30, somewhere in that range. I don't know if I really care that you memorize that number, but just be aware that they're significantly weaker. But even still being only 5 to 10% as strong as covalent bonds, they matter a lot. They're the main reason why, for instance, water boils at 100 degrees Celsius, whereas hydrogen sulfide boils at something ridiculous like -70 or -80 degrees Celsius. Even though it's a heavier molecule with a bigger, fatter atom in it, still there's almost a 200-degree difference in boiling point. And that's because hydrogen sulfide doesn't undergo any significant degree of hydrogen bonding, but water has significant hydrogen bonds. Maybe this is also as good a time as any to remind you that you'll find hydrogen bonding in molecules, especially that have OH or NH bonds. That's something we said at the beginning, but it bears repeating. You're looking for OH or NH bonds. It's not enough for the molecule just to have an oxygen or to have a nitrogen. You get hydrogen bonding when it has OH or NH bonds. That's when the molecule is able both to donate and to accept hydrogen bonds. Well, alcohols are very similar to water in this way. The only time alcohols cannot undergo significant hydrogen bonding is if the R group attached to OH is really, really big. If it's so big that the molecules can't even approach each other significantly, then you're not going to have a significant amount of hydrogen bonding. But certainly your small to medium-sized alcohols will all undergo significant hydrogen bonding. And that's going to affect their properties, mainly in things like boiling point. It's going to drive up boiling points because you need to put in energy in order to disrupt those hydrogen bonds and separate the molecules from one another, which you have to do in order for the substance to go from the liquid state into the gas phase. So that's where hydrogen bonding really comes in. I would say, especially your smaller alcohols like methanol and ethanol, those particularly undergo a high degree of hydrogen bonding, and those two alcohols are not only soluble in water, they're what we call miscible. And I put that word in your class notes, miscible. It means they're soluble in all proportions. You can take any amount of water and any amount of either methanol or ethanol, and you will get just one phase. It will not separate. You will get just one layer. So those have so much hydrogen bonding that they're soluble with water in all proportions. They're what we call miscible. As the alcohols start to get larger than that, then you start to get certain limits on how much can dissolve in a certain amount of water. But all alcohols, unless again the R group is really huge, all other alcohols have some degree of water solubility because they undergo some degree of hydrogen bonding. Let's see. I think that's all I really need to say about that. Where are we at in terms of time? Good. Well, I'm actually going to try to get a little bit ahead. We were only supposed to get through 7.4. I'm going to see if I can't get through most of 7.5, 7.6, and 7.7 today. And then maybe, well, let's at least get through 7.5 and 7.6. And if we have to leave 7.7 for next time, that's fine. And it might mean that there'll be material both on Mondays and Wednesdays classes that will not be on the exam. But I plan to be very clear about that when I'm done with exam material. And I'll say we're starting chapter 9. This is not on exam 3 when that happens. Now we are not starting chapter 9. So we've already talked a fair bit about acidity. We've learned that the degree to which any substance is acidic is exactly the same as the degree to which that substance can give up H+. And alcohols are slightly acidic. They're pretty weak acids. Most aliphatic, meaning alcohols with alkyl groups, most aliphatic alcohols have pKa's round and about in the mid to high teens, generally around the same range as water itself, which is around 16. Phenols are a different critter. So let me see, I actually would like to have more room back if I can. So let's see, let's talk about ethanol. Ethanol is a pKa of, and you'll see I'm looking it up, 15.9. I don't know if I really care that you know exactly what it is, but it'd be good if you knew that they were in the mid to upper teens for most aliphatic alcohols, and they're in the same range as water. So they're about comparable to water in terms of acidity. And what we're talking about when we talk about the acidity of ethanol is we're at the same time commenting on the stability of its conjugate base. And the conjugate base of ethanol would look like this. It would be the ethoxide ion. And so the ethanol can only give up that proton to whatever degree this anion is stable. And how stable is that anion? It could be a lot worse. At least the minus charge is on an electronegative oxygen atom. This is why if you compare the pKa of ethanol to the pKa of like ethane, forget it. It's like 40 or 50 orders of magnitude difference, astronomical difference in acidity, because it's much more difficult to take a proton off of ethane. The resulting anion would be a carbanion, right? It would be a species that is a carbon atom with a minus charge. That's significantly less stable than this. At least here, the minus charge is on an electronegative atom. So that certainly helps. But if we were to compare ethanol to phenol, that's one thing I really want to get across, is that phenol is an alcohol, but it's special. Main difference between phenol and aliphatic alcohols is it's much, much more acidic. pKa of phenol is 10. And when you compare the two, you see they're apart by 6. Remember that the pKa scale is logarithmic because pKa is minus the common logarithm of the equilibrium constant of acid dissociation. So that means if you have a difference of 6, that's really a difference of 6 orders of magnitude. In other words, phenol is 1,000,000 times more acidic than ethanol. And that becomes clear why that is when you look at the conjugate base of phenol. And one of the main points I suppose I'm trying to make here is that in order to think about whether something's acidic or to what degree it's acidic, you must think about its conjugate base. You have to think about what it looks like with the proton removed and ask, how stable is that anion? If it's very stable, then you've got a very strong acid. You know, to go to an extreme, what about something like HCl? We all know that's a strong acid. Well, look at its conjugate base. Its conjugate base is the chloride ion. Doesn't get much more stable than that. It's got a filled electron shell. It's isoelectronic with, I believe, argon. So it has the same electron configuration as a noble gas. So that's very stable. So So this acid is very willing to give up its H plus and become Cl minus. I would say ethoxide is considerably less stable than Cl minus. Again, at least the minus charge is on an electronegative atom. It could be a lot worse. But for that reason, ethanol is much less willing to give up the proton than HCl is. And I mean, HCl, what is its pKa? Like -2? It's through the roof, you know, in terms of acidity. So back to phenol. Phenol, or rather the conjugate base of phenol, the phenoxide ion, is a resonance stabilized species. Let me make that a little better. You could have this resonance form, and there's also this resonance form. Remember, this isn't an equilibrium. I say that for myself just as much as for you guys. But what we're saying is the true structure of the phenoxide ion is a hybrid of all of these structures that we're drawing. It's a mixture of structures at all times. And what we can see is that what we're doing is spreading out the minus charge. So some of the minus charges on the oxygen, but it's spread out so the carbons help to bear the minus charge. Now, I bet the majority of the minus charges on the oxygen, but there is a significant percentage, you could say, that's distributed among these three carbon atoms in that ring. And so that means the carbons help the oxygen to bear that extra electron density. We say the negative charge is delocalized in the phenoxide ion. It's localized in the ethoxide ion. Again, at least it's on an electronegative atom, but it's all on that oxygen. It's localized on that oxygen. Whereas in the conjugate base of phenol, that minus charge is delocalized and shared amongst those four atoms. So that means that phenol is all the more willing to give up that proton and make the conjugate base. That's the main concept that you have to get down in order to understand acidity, is understand that when the acid gives up the proton, it becomes the conjugate base. And that's what you're really looking at. When you're asking how strong an acid is, what you're also asking at the same time is how stable is its conjugate base? They're one and the same question, effectively. And what we're finding is that anything that helps to stabilize that negative charge that you get from removing the proton, anything that can help to do that will make the conjugate base more stable, which will make the acid stronger. And you can see the effect is pretty profound. It's 6 orders of magnitude going from ethanol to phenol. So that's, again, I would say a main topic that I wanted to get across in this chapter is that phenol is an alcohol. It does belong in the same category, but phenol is special because it's so acidic. It's about 1 million times more acidic than your standard alcohols. I just want to go through a couple more examples. Maybe one in comparison with phenol and ethanol. Let's also talk about ethane thiol, since thiols are also covered in this chapter. Thiols in general are also more acidic than alcohols by quite a bit. And that is to do with the stability of the conjugate base as well. If you consider the conjugate base of ethane thiol, it looks like this. Oh, and the pKa of ethane thiol, what is it? 10.6. It's about 10.6. So now we're, a good 5 orders of magnitude more acidic than the alcohol. And the main reason is because we're putting this minus charge in a significantly larger atom. Remember, sulfur is much larger than oxygen. And so now you're spreading out this negative charge on the surface of this big fat atom. It's got more surface area to spread out the negative charge. Remember, like charges repel. And so all of this concentrated negative charge wants to spread out as much as it can. And so it can do that much more effectively on the ethane thiolate ion, which is the conjugate base of ethane thiol. It can do it more effectively than in the conjugate base of ethanol, the ethoxide ion. So that's why you see that significant difference in pKa's. Again, I don't expect you to memorize any of these numbers. That's not the point here. But given numbers like this, I think we can make some pretty good comparisons. And in order to do that, we need to think about the conjugate base. I want to end with one last example, which is I want to compare ethanol. I'll put the pKa's in here. I had to look them up before class. We'll look at 2-fluoroethanol, and we'll look at difluoroethanol, and we'll look at trifluoroethanol. Now, any effect of the fluorine you might think is going to be somewhat removed from the alcohol functional group, because all of them have that CH2 in between. And the reason that is I can't put the, or can I? Would that still be stable? I don't know if that compound exists. I didn't even think of that. I might have to look that up for next time. But you're still going to see an effect of the fluorines. And remember, fluorine is the most electronegative element that there is. So here we have just one fluorine pulling some electron density away. Here we've got 2 of them. That's going to do it a little more so. And then finally, with 3 of them, we're pulling a great deal of electron density away from that. Trying to draw a big old fat arrow over here. Pulling even more electron density away. Again, somewhat limited by being another atom away, but you can still see the effect. Actually, before I go to the numbers, let's ponder just for a second what we would expect to see happen. In all of these, the question is going to be, what does the conjugate base look like? And how stable is that conjugate base? So I'm going to push you. I'm not going to draw out the conjugate base of all of these. I showed you how to do that up here. Just take off the H and write a minus charge. And we're asking, how stable is that anion? Is there anything that's helping it to bear that extra minus charge? And I think that there is, because to whatever extent this extremely electronegative fluorine atom is withdrawing electron density toward itself, it means you're spreading out that extra electron density over more of the molecule. And you're having more and more of the atoms help to stabilize that negative charge. It's effectively the same thing we saw in ethane thiol over here, where we were spreading out the minus charge over a bigger atom, over a larger surface area. It's a very similar effect with these 4 molecules, and that shows up in the pKa. We would expect it to go down little by little as it gets more and more acidic. Remember, with pKa, as the pKa goes lower, the acid is stronger, and as the pKa goes higher, the acid is weaker. That's because of that pesky minus sign in front of minus log of the acid dissociation constant. So I'll say that again. When the pKa goes up, the acid gets weaker. When the pKa goes down, the acid gets stronger. And again, that's because of that minus sign. Anyway, we already know for ethanol, I almost have it memorized by now, 15.9. For 2-fluoroethanol, it's 14.4. So it's an order of magnitude more acidic. 13.0 for 2,2-difluoroethanol. And for 2,2,2-trifluoroethanol, we've got 12.5, which is still a fairly large difference in acidity. It's probably like 4 or 5 times more acidic. So all of this is to say that, that alcohols are not the most acidic species in the world. Certainly carboxylic acids are a lot stronger in terms of acidity, but you can still see some effects of the structure of an alcohol on its acidity. So I think that's probably a good place for us to end today. Next time, I want to pick up on the idea of alcohols acting as bases, since they can do that. They're amphoteric like water. Other than that, have a great day, and we will see you all on Friday.